Okay, so we're going to talk about our volume by cross sections. So remember, if the slices are perpendicular to the x-axis, this is going to be a dx problem. The base, whatever you happen to have for your functions, let's say, for example, we have f on top and g on bottom, then our base is going to be the distance between f and g. So perpendicular to the x-axis would be an upper minus lower problem. Area, if we're talking about a square, is f minus g squared. So you'd have base times height. But your area might not be a perfect square. It might be an equilateral triangle or some other value so that you have a constant times the side squared to come up with your area formula. Your volume is always the integral of area. You can factor out a constant if there is one, and simply use your integration like you would normally do. Now be very careful, this is never going to be f squared minus g squared. If necessarily, you would have to FOIL or distribute, because f minus g quantity squared requires FOILing. It's not the same as f squared minus g squared. If the slices are perpendicular to the y-axis, then it's a dy question. In that case, you'll have a curve that's right and a curve that's the left. And perpendicular to the y-axis is going to get us our base length. For a square, you would then have that same length, again, for side times side. If you don't have a perfect square, then you'll have some proportion typically of f minus g quantity squared. And the constant can be pulled out. You could really memorize it as a constant all the time, because even if the constant is 1, where you have one side times one side. So we need to have a little bit of a refresher on what we have for the area of known geometric shapes. So if I were slicing something that looks kind of like a megaphone or a speaker, and the sides make a perfect square, the area of a square is side times side, or side squared. In this case, my slices are perpendicular to the x-axis, so that means that I'm doing a dx problem, upper minus lower. So the side length is going to be the upper function minus the lower function. Now I'm writing f minus g, but that does not mean that always the f function would be your upper function. You have to use not a formula, but our actual functions, whatever you're given. So be careful about that. Now that means the area of my square, being side times side, is the difference f minus g, all being squared, which could require FOILing. So my volume is going to be the integral of area in this case it was dx because we were perpendicular to the x-axis, and we're going to do the area in this case from A to B. So those are my endpoints. An equilateral triangle, remember, is really two 30, 60, 90 triangles kind of together here. But that means if I have a side length and all these sides are equal, I can find the height by looking at just this one 30, 60, 90 triangle. So the height that I have, we have 1/2 s, is half of the side length from here. I have another side length of s, but since this is a 30, 60, 90, with 60 being the congruent angles of my equilateral triangle, my regular polygon, then I would have 1/2 s across from the 30. The hypotenuse is twice that, so it's s. The long leg across from the 60 is the square root of 3 times the short leg. So root 3 over 2 times s. So that means that the height of my equilateral triangle is root 3 over 2 times s. So the area of the triangle is 1/2 the base of the triangle times the height of the triangle. That means that every equilateral triangle has an area of root 3 over 4 side squared. So since our side length was determined by the distance between our functions f and g, then the area is the same as the square with a different constant of proportionality. This means that my volume, which is the integral of area, from A to B, is simply going to have a different constant of proportionality out in the front, but otherwise be the same integration formula. Now, for semicircles, the base that's sitting between our two functions, let's write this one in terms of y. So our right minus left function, and the cross sections that are out in our three-dimensional space are semicircles. The difference is that f minus g is actually the diameter. So the radius is half of f minus g. The area of a semicircle is 1/2 pi r squared. So the area of my semicircle, in terms of the f and g functions, is 1/2 pi, or pi over 2, times the entire radius being squared. But the radius being squared is not just f minus g, but half of f minus g. So the 2 has to be squared and becomes a 4. And you still have the foiling necessary for f minus g squared. So the area of a semicircle in terms of its diameter, instead of in terms of its radius, is pi over 8 times the diameter squared. So for our volume, constant of proportionality can be factored out. And then we integrate area. And this one we said was a dy. So we'll call this c to d. Now, my isosceles right triangle, if we're on the base, and the base happens to be a leg, then we really just have half of a square, because the 45 and 45 have isosceles legs. So half of a square makes our volume 1/2 of the side squared, and the side being the distance between f and g. Now, if you have a rectangle, rectangles can be tall and thin, shorter and fatter. It really depends upon the proportions of your particular triangle. So even having a rectangle that we say the area is 100, could be a square, side times side, but it could be, in this particular case, maybe it's a 4 by 25, or maybe it's a 1 by 100. So this doesn't have a fixed proportion like all of the other shapes. That means there has to be something given. This means that your base still has to be the difference between your functions, but the height would have to be given to you. So it's either going to be given as a separate function entirely, having nothing to do with f or g, or the height would have to be given to you as some proportion of f minus g. So if this is given to you as something completely unique, your area is still base times height. So your volume, which is the integral of area, could be a completely different height function times the base length of f minus g, which could require you to distribute and simplify or just use your calculator to integrate. Or if they give it to you as some proportion, then if height is a proportion of f minus g, then multiplying base times height once again gives you an f minus g squared, a constant you can factor out. So you would have a different constant proportionality. So be very careful that you're only ever factoring out the constant for any of these problems. You're never factoring out a function. Also, sometimes you're given cross-section problems where they simply tell you the area of the cross-section makes a sinusoidal or some other shape. If they're giving you the area function, you don't have to figure anything out. There is no geometric shape that you're going to use. Remember that volume is the integral of area. dx or dy would depend upon the problem. Perpendicular to the x-axis is dx. Perpendicular to the y-axis is dy. But if you're given area, the only thing your graph would be necessary for is figuring out your endpoints. So an example, finding the volume of a solid whose base is bounded by the circle x squared plus y squared equals 25 with the indicated cross-sections perpendicular to the x-axis. The phrase perpendicular to the x-axis automatically tells us this is a dx problem. That means that we're going to do an upper minus lower to get our base length. In this particular case, we have two different functions. The red function, that's the top of the circle, the green function is the bottom of the circle. So y squared is equal to 25 minus x squared, and y is two different functions. So the equation of a circle is always going to be two different functions, not one function. So plus and minus the square root of 25 minus x squared. So the upper minus lower for my base, or one of my sides, is the positive function, square root of 25 minus x squared, minus the negative function of negative square root of 25 minus x squared. Now minus and negative actually means adding. So my base is 2 square roots of 25 minus x squared. Now the area of a square is just side times side, or side squared. That means that my base and my height are the same thing. So my area is going to be the base length of 2 times the square root of quantity 25 minus x squared, all squared. So that makes my area formula 4 parentheses 25 minus x squared in parentheses. Make sure those parentheses are there so that you're getting the correct area formula as 100 minus 4x squared. If you make a mistake and leave parentheses off, or simplify incorrectly, you're going to lose a lot of points. So we integrate area to get volume. So I'm going to do the integration of 100 minus 4x squared in terms of x, so dx. And I'm going to go from negative 5 to positive 5. And each of my squares would come up perpendicular to the x-axis, would be three-dimensional, popping kind of out of the page of us here. So negative 5 to 5, since both of these are even functions, meaning I have x squared and x to the 0, that means I can really multiply by 2 and integrate from 0 to positive 5, because the left-hand side and the right-hand side are really equal in an even function. So I can do 1/2 of the shape and then double it. So it's going to make this a little easier to simplify. So I'm going to hold that 2, integrate 100x minus 4/3 x cubed from 0 to 5. So I'm still holding the 2. I end up with 500 minus 4 times 125. So 500 again, but that part's divided by 3. So you can kind of think of this as 1,000 minus 1/3 of 1,000. That means I have left 2/3 of 1,000, or 2,000 over 3. Now everything that you do on a free response requires you to write the process that you're doing with correct calculus notation. That means that when I'm finding an integral, I must write the integral and indicate what I'm trying to find. So equilateral triangles, remember we said the formula for the area is √3 over 4 side squared. That means for our shape perpendicular to the x-axis, the side length of my equilateral triangle has to match the base length. That means that my base length is still the same base length that I had before. When I square that base length, I still get 100 minus 4x squared. So the only difference between this problem and the last problem is the √3 over 4. If I were working this problem completely from the original, I would have to integrate all over. I do have to write my integral regardless to show my work. However, since I've already done the integration and found a value for s squared being integrated, the only difference is the constant multiplier on the outside, then I really can go straight to √3 over 4 times the 2,000 over 3. So 1/4 of 2,000 is 500. So I have 500 √3 over 3. Similarly, for the semicircle, we said the area of a semicircle in terms of its diameter is pi over 8 diameter squared. So that's going to make our area pi over 8 times the f minus g being squared, which we have from the previous part A. So that means that my integral is pi over 8 from negative 5 to 5, 100 minus 4x squared dx, and the only difference is I now have a pi over 8 times the 2,000 over 3. So that means I have 8 to cancel into 2,000. So I end up with 250 times pi divided by 3. Now the isosceles right triangle has the congruent legs, but it's really just exactly half of that square. So our area is 1/2 side squared. So we integrate area to get volume. So 1/2 the integral from negative 5 to 5 of 100 minus 4x squared dx is really half of the square that we had before. So 1,000 divided by 3. For the next question, we need to be able to sketch our curve and find our intersections. So if we set x squared minus x minus 3 equal to x, then we have x squared minus 2x minus 3 equal to 0. Factoring equal to 0, we get x and x minus 3 and plus 1. So our intersections are going to be at x equals negative 1 and x equals positive 3. Okay, so if we sketch y equals x, over 1, up 1, through the origin. Notice this is not a square box, so you shouldn't have drawn to the diagonals. That would kind of mess you up if you did. It's the width of like your calculator screen, so they're not proportional, left and right, up and down. Okay. X squared minus x minus 3 is going to intersect at negative 1 and at positive 3. And it's a right side up parabola. So it really doesn't matter that I find the zeros of that parabola. It matters that I can figure out where the intersections are and I know the relationship of the two curves, the bowl up versus bowl down, so my parent functions. Perpendicular to the x-axis is dx. So that means my side length through my base is upper minus lower. We'll start by talking about the square again. So the area of the square is side times side. So my upper in this case is y equals x minus my lower, which is x squared minus x minus 3. And if I square that side length, I get the area of the square. It's extremely important if you're writing this out that x minus the function x squared minus x minus 3 has to have the parentheses or it's incorrect. Writing a minus and assuming everyone will know what you meant, if you don't write what you mean, you're going to lose the points. So I end up with a negative x squared. X minus a negative x is plus 2x. And minus a negative 3 is actually plus 3. And then quantity squared. Remember, f minus g, quantity squared, is not the same as squaring each separate part. So to find my area, in order to do this by hand, I have to FOIL this out. I prefer to use what I call the tic-tac-toe method. To create a table to distribute. So negative x squared times negative x squared is positive x to the 4th. Negative x squared times 2x is negative 2x cubed. And negative x squared times 3 is negative 3x squared. Following that pattern, I would end up with negative 2x cubed, positive 4x squared, positive 6x, negative 3x squared, positive 6x, positive 9. So my tic-tac-toe means I have a corner of x to the 4th. I can connect the x cubed along the diagonal, the x squareds along the diagonal, x to the 1st power, and my constant. So I'm actually integrating from x is negative 1 to x is 3, the function x to the 4th minus 4x cubed minus 2x squared plus 12x plus 9 dx. For expediency's sake, we'll let you finish the fundamental theorem separately or check your work on your calculator for this part. You don't typically have to integrate something extremely complex when you're doing the area and volume problems unless you're using your calculator. So the setup for the rest of the problems is really just the difference, including that integral constant of integration in the front, the proportional constant. So root 3 over 4 from -1 to 3. And then the rest of the problem is exactly the same. So for the semicircle, the volume would be pi over 8 times the integral from -1 to 3 of x to the 4th minus 4x cubed minus 2x squared plus 12x plus 9 dx. For the isosceles right triangle, the proportionality would be 1/2 of the square. So the integral from -1 to 3, x to the 4th, minus 4x cubed, minus 2x squared, plus 12x, plus 9 dx. Now before we move on, I want to talk about a problem like this that involves your calculator really to do the integration. Because learning how to use your calculator appropriately is extremely important. So, setting this up for calculator use, we would still have to graph and find our intersections for x. And if we're doing a dy question, then we'd also need the y points. However, if I were working this on my calculator after I had found x equals -1 and +3 with my calculator, finding the intersections, and I determined based on the graph from my calculator that x was the function, in fact, that was on top, I may have entered these into my calculator in order that you see them on the paper. So for my own self, I could make the note that this was y1 and this was y2. So since I've labeled for myself the y1 function and the y2 function that I entered, remember calculator notation is never acceptable on the AP exam. So what I could do, however, is say that I'm going to let f be, or f of x equal x, and g of x equal the function x squared minus x minus 3. That allows me to say that my area is f of x minus g of x quantity squared. Now, if the AP exam or the question that I give you has already labeled the functions with different letters, you must leave those letters alone because they're grading you off using the function notation given. So my integration from -1 to +3 has parentheses of its own, but I will be doing the function f of x minus g of x quantity squared. So the integral is not being squared, the part inside of the integral notation is being squared. That would then allow me on my calculator to simply type in the -1 to 3. Your calculator gives you the open integral parentheses. And based off the fact that my f of x equal to x needs to come first, I would have to have a parentheses y2 minus y1 quantity squared, close parentheses, and then dx. So on my calculator, you would see the answer is 34.13 repeating, or 512 over 15. So 3 decimal places of precision, or the exact answer. So that means that my answer for each of the other problems can simply be that answer multiplied by the respective constant of proportionality. Okay, for the next problem, the base of a solid is the region between one arch of y equals sine of x. So I'd have to know how to do that without my calculator. So one arch of sine of x means you can kind of pick where you'd want that to be. I'm just going to start mine at the origin. And the x-axis. So for my ease, this is going to be my base. It's going to be starting at the origin. So that means, since each of my bases perpendicular to the x-axis as an equilateral triangle, then this is how my three-dimensional shape would come about. So if I were to try to sketch this shape, try to give you an idea of what it would look like. The equilateral triangles are smaller pieces of it. I could try to let you see that if we have the outside line here, straight line with an arch, within this line going down the center would be the peaks of these triangles. So from a side view, looking at the straight side, these would be slanted up, but they would be getting smaller at each end. And so on the flat side, the x-axis side, you'd simply see perfect slants going up at an angle of 60 degrees. On the arched side, from that view, you would also see smaller and smaller pieces, so the higher part in the middle, smaller part at the ends. So it would also have a curved top, because the triangles are shorter each way, and it would slice up and down. So the area of the equilateral triangle is √3/4 sides squared. The length of each of those sides is going to be the top, which is sine of x, minus the bottom, which is 0. Because remember, the x-axis is y equals 0. So that means my area is √3/4 sine squared x. So my volume, I can factor out the √3/4. We're integrating from x is 0 to x is pi, and we're integrating the function sine squared of x dx. Now remember, you might not have had to draw sine with your calculator, and you can simply put that into your calculator as y1. If y equals sine of x is in your calculator as y1, then the calculator part of this, which is not allowed to be part of your answer on an AP exam, would be √3/4, integrating from 0 to pi. You have your integral with the dx notation. It has parentheses already, so match that. Your calculator typically does correct notation. If you mimic that on your exam, you'll be doing well. So that means that I can really just do the y1 function, and the y1 function is already stored in your graph as sine of x. I can just square that y1 function. So it's a little easier if you've stored the function into y1 or y2 than if you have to do this version. So I have my integral parentheses. I have parentheses to square the sine function, and sine of x has its own set of parentheses. This is much worse than if I just put this into y1 and I get to do the easy version here. So if I use my calculator and I type y1 as sine of x, since I'm only using the y1 function, I really don't even have to change anything else, but it is good practice to clear out. Then I'm going to use the fraction feature to enter the square root of 3 over 4. The integral, which we said the shortcut was to do the math button and then the number 9, from 0 to pi. Please do not put an approximation for pi in there because your final answer might not be as accurate. And since sine is my y equals function, I can simply get my y1 and square the y1 function. So that's sine being squared, dx. So we found our volume to be 0.680. Even though that's a 0 at the end, you are required to list that decimal place of precision. You may not write 0.68 and get full credit. You're going to lose a point if you do. The next one, the base of a solid is a region bounded by the upside down parabola, 1 minus x squared. So my zeros are at positive and negative 1. Not very good at sketching. Oh, I'm going to try again. I give myself another point to aim at, that might help. Again, it might be the tablet that I'm using. Okay. Okay, so the other function that we're using is x to the 4th minus 1. X to the 4th is very similar to x squared. It simply will grow flat in the center part, because instead of taking 1/2 and squaring it, which gives us 1/4, we're going to take 1/2 and raise it to the 4th power, which gives us 1 over 16. So we have a much flatter function for this part of it. But we still have the intersections where 1 and negative 1 would give us solutions. Just a more rounded or flat shape prior to that. Cross sections, it says, for our area. So we have our area here. Perpendicular to the x-axis means the length of the base is upper minus lower dx. So squares. Squares means that we have our areas just side times side. So let's say we're going to let f of x equal 1 minus x squared. G of x equal x to the 4th minus 1. This prevents us from having to do f minus g is the parentheses around the f function, parentheses around the g function, and then another set of parentheses for squaring, and technically a 4th set of parentheses for our integration. It allows us to simply say we're integrating from negative 1 to 1. F of x minus g of x being squared as our side squared dx. That would get us full credit for everything in the setup of that problem. Now, I'm going to do this one by hand because we have an interval of negative 1 to 1, which is symmetric to the y-axis, and both of our functions are even functions symmetric to the y-axis. So our f minus g would be 1 minus x squared in parentheses, minus the parentheses around x to the fourth minus 1. So 1 minus x squared, distributing the negative makes minus x to the fourth plus 1. So 2 minus x squared minus x to the fourth. This whole part would then have to be squared. So using our table method, 2 minus x squared minus x to the fourth, 2 minus x squared minus x to the fourth. So I'm going to multiply like using a multiplication table. And the reason I wanted to do this one that it's being even is because what I can do is do the 0 to 1 portion and simply double it. But I'm integrating not just one of the functions, but the area function, which turns out to be 4 minus 4x squared minus 3x to the fourth plus 2x to the sixth plus x to the eighth dx. So I don't have a linkage error, so I have to carry that 2 with me the whole time. Then I would get 4x minus 4/3 x cubed minus 3/5 x to the fifth plus 2/7 x to the 7 plus 1/9 x to the 9th, but from 0 to 1. Since this is a polynomial, substituting in 1 and then 0 gives us a 0 for the bottom part. So I don't have to show the minus 0. I have to keep the 2, and then substituting in the 1, I get 4 minus 4/3 minus 3/5 plus 2/7 plus 1/9. I want to put some emphasis on there. I could throw in a minus 0. But that would be my FRQ answer. And that's much easier, even if that's all I have to do was to substitute in 1 and -1. It's still much easier just to substitute 1 and 0 and not have to worry about the signs on the -1 being put in there. Again, you can, since you have this one as your y1 and this one as your y2 in your calculator, you can write this part on your paper for credit. And then if it's a calculator problem, simply use your calculator to evaluate the whole thing. Only do things by hand if you absolutely have to. Okay, so this last problem, the base of a solid is the region bounded by one arch. There is only one arch. Bounded by y equals square root of x and y equals x squared. So the square root of 0 is 0, the square root of 1 is 1. Square root of 2 would be 1.4-ish. As long as you can get the general shape here. Y equals x squared. 0 is 0. 1 is 1. -1 is 1. And we can do our parabolic shape. And really, without having to set the two functions equal, just based off graphing, we could find a very accurate intersection of 0 and 1 that we're 100% certain are true because we actually evaluated those points. Now, perpendicular to the y-axis, that's different. Your little guy's going to scream, oh no, no. Okay, so that means that we have to convert this over. Now, it just so happens we have the point 0, 0 and the point 1, 1. So you would kind of get away with the fact that x is going from 0 to 1 and so is y. But you really need to watch this because it's not always true. We're going to do the y ones because we're doing perpendicular to the y-axis. That means our problem has to be in terms of y. So if y equals the square root of x, that means that y squared is equal to x. If y equals x squared, then y is equal to plus or minus the square root of x. Sorry, I said that backwards. Then x is equal to, plus or minus the square root of y. Now you can't do both of those functions if they both aren't relevant, and for us they are not both relevant. We are doing x equal to y squared, and x equal to positive or negative square root of y, we're using the positive x side. So x is a positive as opposed to x being a negative. So watch your quadrants. We are taking this with respect to y, so that means that we're going perpendicular to the y-axis this way. So we're going to get our right minus left. So the right-hand function is x equal to the square root of y, and the further left function is x equal to y squared. We are doing semicircles. The diameter extends across the region. So this is what our little semicircles look like here. So my diameter is right minus left. The area of a semicircle in terms of diameter is pi over 8 diameter squared. That means we're going to integrate the pi over 8 constant factored out from y is 0 to y is 1 in terms of y, and the diameter being squared is the square root of y minus y squared, quantity being squared. Now, in using your calculator, you're going to put the pi over 8 in. So you're going to go from 0 to 1, but you're going to put these into your calculator in terms of x. Remember, it really doesn't matter what letter you use as long as you are consistent with the letter throughout the entire calculator process. Okay, so remember, you're going to get a parentheses automatically for the integration symbol. So that means you're going to have to put your own parentheses in. You'll get the square root of x minus x squared. You have to remember to close that and square the whole thing so that you have your f minus g squared. So my pi over 8, I'm going to do alpha f1 to get the fraction. Pi over 8, math, 9, 0 to 1. I need another parentheses, and then the square root of x minus x squared. Make sure you don't accidentally put everything under the radical. And then I have to close that f minus g quantity squared, and then dx. Now if you prefer to use the letter y, you can use y the entire time. You'll have to use the alpha button to get the variable y, which is above number 1. That's not the same as your y1 function. So you could kind of tell that we're going to get a really tiny area and a little tiny volume because of the fact that this all fits within that 0 to 1 space. But the pi over 8, so we get a volume of 0.050.